Testing? Testing? All right, so we're continuing in Chapter 6 on page 222, looking at the case study, random number generation. And that does continue from 222, 223, 224, 225, with continued narration for line-by-line course dissection. So we're going to simulate rolling a six-sided die. We have a dice, and it's numbered 1, 2, 3, 4, 5, 6. We want to roll that dice and come up with random numbers. Now, rolling a six-sided die simulates, in this program, we're going to repeatedly, 20 times, roll the dice and print whatever face value came up, a 6, a 5, a 4, a 3, a 2, or a 1, in a field width of 20 characters. So remember, about 20 characters, our content will print right justified in that field width of 20 spaces. Another 20 spaces, 6 space value prints right justified. So it looks like we're tabbing across with about with the field width in each tab space position of 20 characters. When we're done printing out 5, 1, 2, 3, 4, 5 values, then we check if counter is mod 5. So when we look at the integer remainder dividing by 5, if that's equal to 0, well, 1 divided by 5 is not, 6 divided by 5, or 2 divided by 5 is not, but when I divide 5 by 5, I get a remainder of 0. So that triggers, we have printed 5 field widths of 20. So I've got 5 columns, and I'm ready for a new line. And that's what happens then when counter is evenly divisible by 5, and we print a new line. And then print in columns 20 width 5 times across, and when we have our 5th column printed, we print a new line. So a couple new things there for us. We have the random functionality going on. Talk about that a little more in detail, and then some type of tabbing control in our if counter mod 5 is equal to 0. That forces us to print the new line. Our function prototype for the rand function is located in the C standard library. So we've included that header, which then also contains the function prototype for rand. So function prototype has been is known by the compiler. We're going to look at line 12, which is C out, our set width, calling our function rand, found in the C standard library header. And let's just look at this a little bit. We did include the C standard library in line 5. It contains the prototype for our random function. So we can call random function. Calling random function, this will generate random function. Modular 6 will randomly produce numbers 0 through 5 as an integer type. So with this, we call 6, or that position, our modular, and whatever value there, we call that the scaling factor. So I want to scale my returned integers 0 through 6. Well, it's going to return 0 through 5. So if I modular arithmetic by 6, mod into our random numbers, I'll have the number of integers returned 0 through 5. 0 through 5, so any number 0, 1, 2, 3, 4, 5 plus 1 would be my integer values representing the face values of the die, 1 through 6. So I've offset or my shift value of 1. So random %6, a scaling factor, gives me the numbers 0 through 5. If I'm working with dice, I'd like my face values to be 1, 2, 3, 4, 5, or 6 as I toss the dice. So I'm going to shift 0 through 5. 0 plus 1 would be 1. 2 plus 1 would be 2. 3 plus 1 would be 4, and so on. 5 plus 1 would be 6. So I've scaled and shifted using the random function to get random numbers with my representation in this program, face values 1 through 6 for my 6-sided dice. So let's see what happens. Okay, so this is a shared data file. So you can copy and paste this data file into your new project. Open figure 6-6.cpp file and delete any of the default code and paste in your shared data file. Be sure to set your project properties, C++, precompiled headers to not using precompiled headers, apply and say OK as our regular standard setup, and then file save all. All right, we are including IO stream, IO manip, and standard library, which contains our prototype for our random function, which we are calling. We have not declared its definition, so it has to be included as an include header file, knowing that C standard library contains our prototype for our random function. Int main, begin end of main. We're going to call a for statement. An unsigned int counter is set equal to 1. As long as counter remains less than or equal to 20, we'll continue to increment counter. So 1 is less than 20. We're going to begin to execute the loop. We're going to make sure that we have made arrangements to generate a random number from 1 to 6, and then we're going to output that. So cout, set our width, and then place the value of 1 plus the number returned by random, which will be a random integer from 0 to 5. So our scaling factor, we have a range of 0 through 5 will be returned. I'm going to add 1 to it. So I've now made arrangements for an output of 1 through 6. My scaling factor says return for me numbers 0 through 5. And numbers 0 through 5 plus 1. 0 plus 1 would be 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. And 5 plus 1 is 6. So I have my face values 1, 2, 3, 4, 5, 6. Outputting a value, I shook the dice and I've got a value, let's say it's 3, a face value of 3. That's been printed. And then it tests. I'd like to have 5 columns across. So if counter, which is 1 right now, mod 5, 5 goes into 1, 0 times with the remainder of 1. So the remainder is not equal to 0. So I'm not going to print a new line. I will print a new line, however, when counter is evenly divisible by 5, that is, the remainder would be equal to 0. Then I'll print a new line. So it's a way, this little technique is a way of tabbing across your page, forcing a new line after 5 field widths of 10, I guess. So let's see what happens. Control F5 does not call the debugger. F6, 6, 5, 5, 6, 5, 1, 1, 5, 3, 6, 6, 2, 4, 2, 6, 2, 3, 4, 1. Okay. Well, that looks like pretty evenly face values 1 through 6 have been tossed as I attempted to randomly generate face values of 1 through 6 by simulating tossing a dice. Well, there's also simulations where we want to simulate random numbers for tossing a coin. So let's just edit this a little bit. I want to simulate tossing a coin, heads or tail. And we could let heads equal 1 and tails equal 2. So my scaling factor is going to be 2. So that will produce random integers from 0 to 1. So if I have 0 plus 1, that'd be 1, and 1 plus 1 would be 2. So I could be arranging to test if a 0 or a 1. If a 1 or a 2 were returned, then I could have that represent, well, if it's equal to 1, it's head. If it's equal to 2, it's tails. So let's see what happens. I should only have 1 or 2 as output values generated from my random toss of the simulation of a coin, heads or tails. So there's tails, tails, head, head, tails, head, 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 tails, 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 head, tails, head. Remember, we'd have to reconfigure this and do some more coding for a real simulation, but you're understanding that we are simulating the cost of a coin where we've made arrangements for the random number returned 1 to equal the face value of a coin of heads, and 2, the random number 2 generated would be the random generation of a simulation of the tails toss of a coin. Well, then we might have a need, if you're doing some gaming techniques, to write a program that randomly predicts the next type. Write a program for that will randomly predict the next type of spaceship out of 4 possibilities that might fly across the horizon in a video game. And that would require random numbers generated from 1 to 4. So again, if you're writing a game and you want to randomly predict the next type of a spaceship, the user can pick 1 of 4 different spaceships, different types, that will fly across the horizon in a video game. We would need to have random numbers generated in the range of 1 to 4. So let's set that scale factor to 4. random, call the random function mod4 will generate random numbers 0 through 3. 0 plus 1 would be 1. 1 plus 1 would be 2. 2 plus 2 would be 3. And 3 plus 1 would be 4. So I'm able to simulate randomly generating spaceships, and the user could type spaceship 1, spaceship 2, spaceship 3, or spaceship 4 to select a different type of spaceship to fly over the horizon. Let's see what happens here. We should have only numbers 1 through 4 randomly generated. And there's 2, 4, 3, 1, 2, 1, 3, 3, 3, 1, 2, 2, 2, 4, 2, 4, 4, 3, 4, 1. So it looks like we have been able to write code using the random function, a scaling factor, and a shift value that will allow us to control that random number generated to simulate tossing of a coin, tossing 6-sided dice, or choosing one of 4 special different unique spaceships to fly across the horizon in your gaming program. Now just look at these numbers closely. 4, 2, 3, 1, 2, 1, 3, 3, 3, 1, 2, 2, 2, 4. That last line, 4, 4, 3, 4, 1. Let's run this program again. Control F5. And there's your 4, 4, 3, 4, 1. Let's run it again. Last line, 4, 4, 3, 4, 1. Well, let's run it again. Last line, 4, 4, 3, 4. It looks like every time I run it, I'm getting the same generation of random numbers. Yes, the numbers are within my specified range, 1 through 4. But each time I run it, I would expect that it generate a new set of random numbers. Now, this is a concern. At this point, we're able to generate random numbers on the first execution of our program, and after that we call this pseudo-random numbers. It's not truly random. Actually, the second time through, if you know the technique, you would be able to predict what random numbers are going to be output, because when I run again, it's the same random numbers generated. So you can read about this in upcoming discussion. For now, we're going to continue with the next sample of code. Rolling a 6-sided die 60,000 times begins on page 224. Okay, so on page 224, we have the rolling of a 6-sided die 60,000 times. So we're going to, again, simulate through code this scenario of rolling and counting the occurrences of rolling a dice 60 million times. It simulates rolling a 6-sided dice 60 million times. We're including IO stream, IO manip, standard library, which contains our prototype for our random functions. So the prototype is known to the compiler, and we can call it random at any time. In main, begin, end. we are declaring frequency 1, frequency 2, frequency 3, 4, 5, 6. Frequency, we're looking at the count or the number of occurrences for a face value of 1 when I shake the dice. This is an unsigned int, so it's a positive integer. And frequency 2 is keeping count of the accumulated number of times that I rolled a face value of 2. Frequency 3 is an integer keeping track of the number of times that I rolled a face value of 3, and so on. So face value of 1, 2, 3, 4, 5, 6, the number of times that I rolled each face, I initialized to 0. I haven't rolled any face values yet. And then I'm declaring an integer value of by the name of face. I have a for statement. For block. The for header, for unsigned int, it's a positive integer. Roll is assigned 1. While row is less than or equal to 60 million. Now, this technique with the apostrophe is a special technique for C++. Where on page 225, you can represent the integer value of 60 million as 60 million in a program, but we can't really type commas. When we type a comma, remember that's a delimiter, so we'd be looking at 60, 0, and 0 as 3 integer values. Typing numeric literals with many digits can cause errors. So to promote readability, we can insert between groups of digits in numerical literals the digit separator, which is our single quote character. So for example, 60 million represents the integer 60 million, but avoiding commas because they have special meaning, and the single quotes are used rather than commas. So C++ treats the commas as our comma operator, and the value would be rightmost expression. Ooh, would be interpreted as 0, so we'd have an error issue. So we promote using the digit separator, which is our single quote character. So this looks a little bit different. 60 single quote, 000 single quote, 000. But as I hover over, you see that the system is interpreting this as an integer of 60 million. So we're going to continue to roll as long as roll incremented by 1, it remains less than 60 million. Face value is going to be assigned. So face is going to be equal to 1 plus, remember, random %6 returns a number 0 through 5. If I add 1 to a number 0 through 5, I'm going to assign face a number 1 through 6, representing the face values of my dice. 1, 2, 3, 4, 5, 6. Determine the roll value 1 through 6 and increment appropriate counter. Remember that frequency 1 is keeping track of the number of times I roll a face value of 1. Frequency 2 is keeping track of the number of times I roll a face value of 2, and so on. So if face is assigned to 1, a random number from 1 to 6, then switch on face. If face is equal to 1, I'm going to process the switch. Case 1, I would increment the count, frequency 1, for a face value of 1, and then break out of the case, break out of the switch, and return to the top of the 4, and roll is now equal to 2. Roll 2 is less than or equal to 60 million, so I will assign face Random with the scale factor will produce integer numbers 1 through 0. If I add 1 to a random number 0 through 5, I'm going to get a number 1 through 6. So let's say that face is equal to 3 this time. If face is equal to 3, I'm going to switch on face's value of 3. Case 1, it does not match. Case 2, it does not match, but case 3, yes. So I'm going to process the case 3 and increment frequency 3. Incrementing frequency 3 increments the number of times that the face value of 3 has been rolled. And frequency 3 was initialized to 0. This is the first time we rolled a face value of 3. So now frequency 3 is equal to 1. I break out a case 3 and return to the top of the 4. Roll is now equal to 3. Roll is less than 60 million. Face is equal to, I'm going to generate another random number 1 through 6, indicating that I toss the dice and have a face value of 1 through 6. Let's say that face value is equal to 3 again. I'm going to switch on 3, case 3, frequency is incremented, and frequency was 1, so now frequency 3 is equal to 2. So I rolled a face value of 1 and 2 face values of 3. I break out of the case, return to the top of the 4, and continue to simulate the rolling of a dice with base values 1 through 6. Each base value is determined and incremented when rolled. I continue until I exceed 60 million. Then we're ready to print out our summary report with a base and frequency column headings. We're going to output 1, 2, 3, 4, 5, 6, indicating the face value of the dice and its frequency count at the end of the program. Let's see what happens when we execute. It does take a little bit of time to process the simulation of rolling our dice 60 million times. And my face value 1, I had 9,999,294 face values of 1 tossed in 60 million tosses. A face value of 2, I had 10,002,929 rolls of a face value of 2 in 60 million tosses. You can see that it's fairly equal, that it was a equal distribution between each of the face values. Interesting, but let's run again. And after simulating rolling the 6-sided dice 60 million times, we have the same random number count of tossing face values 1, 2, 3, 4, 5, and 6. So again, pseudo-random numbers are generated. If you know this, you could begin to determine some predictability in the randomness of generating numbers, and that would lead to insecurities within our code. We have to find a better solution. So on page 225, 226, 227 through 232, we have a discussion of another alternative way of attempting to generate true randomness of numbers. And we have another game simulation with our case study on page 228. So you are going to be able to skip, I'm going to skip these pages, expecting that you are reading the dissection of the code of the last program that we looked at in the narrative of the book and running and executing the source code. Excuse me. Until you feel comfortable with its process. But we are going to skip 228, the case study, the game of chance, through the top of page 232. You're welcome to read through that material. You're welcome to run and execute the student data file shared, but I'm not going to discuss those pages in detail at this point. We are, however, going to continue with section 6.9 and attempt to determine true randomness of number generation for C++. So random function does not have good statistical properties and can be predictable, rendering it less secure. C++11 provides a more secure library of random number capabilities that can be produced non-deterministic random numbers, a set of random numbers that isn't and can't be predicted. Such random number generators are used in simulations and security scenarios where predictability is undesirable. So even in any gaming program that you would design, we really don't want to allow for any predictability. So we're emphasizing now, how are we going to produce true random number generation? Random number generation is a mathematically sophisticated topic for which mathematicians have developed many random number generation algorithms with different statistical properties. For flexibility based on how random numbers are used in programs, C++ provides many classes that represent various random number generation engines and distributions. An engine implements a random number generation algorithm that produces pseudo-random numbers. The distribution controls the range of the values produced by an engine and types of those values, integer, double, and the statistical properties of the values. In this section, we'll use the default random number generation engine, which is default random engine, and a uniform int distribution, which evenly distributes pseudorandom number integers over a specified range of values, which is exactly what we were doing, but we ended up with non-randomness, some predictability. The default range is from 0 to max value of an int on your platform. So now, using the default random engine and the uniform int distribution to roll our six-sided die, line 13 creates a default random engine object named engine. Its constructor are argument seeds the random number generation engine with the current time. Now, think about the current time. It's constantly changing. So if I ask for the current time right now, it's different than the current time from right now. If you don't pass a value to the constructor, the default seed will be used and the program will produce the same sequence of numbers each time it executes. Think of this as a useful tool for testing purposes. So if you can run the same random number generation for testing purposes, it allows you to test your logic and other calculations within your program with control. And then you can feel confident setting your seed and running your random number generation. So line 13, let's look at that. Line 13, default random engine. Engine is going to be an object of default random engine, and engine is going to be assigned a unsigned int for time 0. Time 0, you can read in the narrative, is a way to capture the time at this point. And we're seeding our random number generation at this point. Line 14 creates random int, a uniform int distribution object that produces unsigned int values in the range of 1 to 6 in our example. Could be 1 to 2 in our coin toss example, 1 to 4 in our spacecraft gaming application. The expression random int engine in line 19 returns one unsigned int value in the range of 1 to 6. Line 14, uniform int distribution, unsigned int. We have a random int object, which is maintaining our range 1 through 6. We go to line 17. We're in a for generation. Our for loop counter is initialized to 1 while it's less than or equal to 10. We'll continue to process in increment counter. Pick a random number from 1 to 6 and output it. See out in your field with a 10. Random int, we're seeding it with the engine seed value of the current time. And random int is going to return then, seeded with the current time, values, a value from 1 through 6. And then we have our tabbing technique again. Let's see what happens when we run this program. Now this is your shared file, figure 6_10. I removed all of the default code for figure 6_10 CPP and pasted the copied code from my shared file. I made sure the project properties were set for C++ with no pre-compiled headers. Apply and say OK. I'm going to save all with those changes and execute Control F5. We have 2, 3, 4, 1, 1, 6, 6, 1, 2, 4. Try to remember those 2, 3, 4, 1, 1, 6, 6, 1, 2, 4, and let's execute again. Control F5. 4, 4, 1, 3, 6, 1, 2, 5, 2, 1. That looks different. Are we truly generating different, unique, random numbers within our range of 1 through 6? Let's execute again. 5, 2, 6, 6, 2, 3, 3, 5, 6, 5. Yes, it looks like we have achieved a way of coding true randomness using new and enhanced techniques in our newer versions of C++, which includes the default random engine and the uniform int distribution. Now, not so difficult. Remember, in our first example, we had this is figure 6_6, and we were introducing ourselves in line 9 to the random function. Random %6. Remember, that was our scaling factor. What was the range that we were wishing to have our numbers returned? So we wanted to have 0, 1, 2, 3, 4, 5. That's 6 values. And we wanted to have the integer remainder when we divide by 6. And we ended up with 0 through 5. We add 1, so we're offsetting with our shift factor. So we have a shift factor and the range we're looking to manipulate. So here we have, with our random int as a uniform int distribution, what's the distribution range that we wish to cover? Well, we wish to have a random integer returned in the range 1, 2, 3, 4, 5, 6. Random int as an integer will return a random integer between the range and including 1 through 6. So there we've set our range or our offset. And the default random engine by its variable name in this case, is our seed, which assures that we're sending a value to start up with a type of randomness on the current type. A moment later is a different time. A moment later is a different time. So we're seeding our random generator with a different seed each time we run the program. Although remember that on page 232, if you don't pass a value to the constructor, the default seed will be used and the program will produce the same sequence of numbers each time it executes. This is useful for testing and maintaining your programs. Line 13, if we didn't send a value and initialize our constructor engine as a default random engine, then the default value would be used and your program would produce the same results each time you run it. So, information to read, study, review, but for now, you should feel comfortable using our class template uniform int distribution to mimic any of your random generated required program applications. And we'll be talking more about class templates in the future. My lecture my next lecture will continue in Chapter 6. And as always, please return to D12, where our unit lesson plan is Unit 6 at this point, and all homework projects, tests, and due dates are listed there. And thank you very much.